Good morning, all of you. So let us now start the topic. Last time we were discussing about simple linear regression. Let me just share the file actually. All right. So we were talking about the simple linear regression, and we developed the model also for machine learning for simple linear regression also. Okay. Yeah. So this was the equation for simple linear regression, in which y is, let's say, dependent variable and x1 is an independent variable. The point is that there is only one independent variable on which this dependent variable is dependent. Now this is simple linear regression. We carried out the discussion based on this, right? I think I will now come to let's start with the multiple linear regression. I will describe briefly the code also for simple linear regression, and then I will come back to multiple linear regression. Now what happens in multiple linear regression? In multiple linear regression, as there is only one variable, which is x1, but in multiple linear regression, so y, which is a dependent variable, will be dependent on x1, x2 up to xn. So there may be n number of independent variables, right? I think I covered these things also: linearity, homoscedasticity, multivariate normality, independence of errors, and lack of multicollinearity. In a particular data set, when you have to apply the linear regression, the data set must you must make the assumptions that the data set follows all these characteristics, right? So I have already gone through this yesterday. Okay, there is one before I talk about the dummy variables and dummy variable trap. Let me show you the data set which I will use for the multiple linear regression. Stop sharing this. Okay, this is the data set that I will use. Just widen up the. Okay, this is state and this is profit. So there are, I hope this Excel file is visible to you, right? So this data set is actually belongs to 50 startup companies, right? The name of the companies is not there, but the data is there. We have to develop a machine learning model based on this data, so that once it's a kind of venture capitalist fund. So based on that, the fund company is actually making an assessment that in what kind of companies should they invest. Now they have, let's say, hired you and asked you to develop a machine learning model based on this data, so that you do some analysis of this data and give a presentation, because the expenditure. So this is a kind of revenue and expenditure statement. This is R&D spend. So 50 companies are. This is the data. The companies are spending on R&D. This is the administration spending, marketing spending, and this is the state, let's say. So if you look at, there are 3 categories of states: New York, California, and Florida. Based on which company is where, that will also matter in the profit statement, in the profit, ultimately in the profit. So that's how, this is our dependent variable, and this is the profit, all right, companies are making. Based on this dependent variable and these independent variables, we have to make we have to develop machine learning models, so that the guidance can be provided to the fund manager so that in what kind of companies it should spend. And of course, the point is that you have to maximize the profit. And the important thing is that the fund company will not only invest in these 50 companies, right? Had they been looking for investment only in these 50 companies, you could have sorted this column, and of course you will try to invest in that company for which the profit is maximum. What is the aim? The aim is that you have to build a machine learning model, right? For example, if a company is spending R&D spend, how the profit, what is the effect of R&D spend on profit? Or administration spend, what is the effect of spending on administration on the profit, right? Marketing spending, how it is related to the profit, or how it is related to the earning. And if a company is in New York or California or Florida, how the profit varies, right? So you have to make an assessment, and the important thing is that the fund company has not to invest only in these 50 companies. Based on this study about companies, they can invest in other companies also. So the task is to build a machine learning model, and you will see that there are 4 independent variables and 1 dependent variable, right? R&D spend, administration spend, marketing spend, and state. These are the independent variables, and your profit is the dependent variable. So this is definitely a multiple linear regression problem where you have to estimate the profits based on these independent variables. So let's see how the things can be developed. All right. Before I come to the code part, see this. All these are you can have a look at the data. Once you have the look at the data, you will see that there is no missing data as such, right? This is 0, might have not spent anything on marketing on the marketing spend, but otherwise there are no missing values. And this is the state, this is the categorical data, right? So you will have to encode the 1, 2, 3, and 4th column as categorical data. That means those lines of code you will have to do the pre-processing, and in the pre-processing you will have to take care of this categorical data. And how many categories are there? There are 3 categories: New York, California, and Florida, right? So you will have to encode accordingly. Now let's look at the. So this is about the data set that we will try to handle. And let's come back to just a minute. I will share the PDF file. Yeah. So this is the, let me go to the view screen. Okay. So this is the kind of data set. These are the columns in the data set that I just showed you. Profit is there, R&D spend is there, admin is there, marketing is there, and the state, New York or California, and the 3rd state is also there, which is Florida. Now you can perfectly relate this data set to this equation where y equal to b naught, which is a constant. X1 can be R&D spend, X2 can be administration spend, X3 can be marketing spend. Now the question is that what should be put here in the mathematical equation? Because New York, California, or Florida, these are dummy variables. These are also known as dummy variables. These are known as the state. These are known as the categorical data, but we will replace this categorical data with dummy variables, right? But the question is that how should we put this in the equation, right? So we will have to encode the categorical data in the form of dummy variables. So how that the encoding is done? For example, this is New York and California. Third option is also there in our data set, but I'm just taking an example of two states, New York and California. Wherever New York is there, put 1, and against that in California, put 0. And wherever California is there, put 1, and against that in New York, put 0. So that's how the encoding is done, right? Now we can change this equation, and these are known as the dummy variables. Okay. Now we can change the equation, multiple linear equation as y equal to b0, b1 x1, b2 x2, b3 x3, and b4 d1. Let's say I'm using d1, which is a dummy variable, which is the first dummy variable for New York State, and b4 is the coefficient, right? It is, you are not supposed to include the last variable, because you see, if New York is 1, California will be 0. That means the two variables are correlated with each other. If you will try to put both the variables in our equation, then it will it will not follow the multicollinearity assumption. It will break the multicollinearity assumption. So we will, and definitely we can, whatever from the New York information, dummy variable, we can always get the information about the California. And this information, if you are putting D1 for New York, the information about the California will be present in B0. The question here is that what is this B0 doing here, right? So about this California, this will come from B0, and D1 is for New York. All right. The point is that whenever you are encoding the categorical data, one of the dummy variables will be left out. If there are, let's say, 10 categories, so you will include 9 dummy variables, you will leave 1. If there are 100 categories, you will include 99 variables and you will exclude 1. All right. Now, okay. There is a problem in handling the dummy variable, which is dummy variable trap. I was just trying to explain when I was trying to explain that you have to put the dummy variable for one category. You have to avoid for the other category. But let's say if you put D5 also for the California state also. Now D2, actually it has to be D2 here, not D5. So D2 equal to 1 minus D1. So that means D1 and D2 are interdependent with each other, right? The phenomenon where one or several independent variables in linear regression predict another. So if we know D1, we can know D2 in the and see, this equation will not follow the multicollinearity assumption, lack of multicollinearity. So this is having lack of multicollinearity. So as a result of this effect, the model cannot distinguish between effects of D1 from the effects of D2, right? When you are training the model and when you are using the linear regression class, then the model will not understand the correlations between different data. If you will try to put the last variable, if you will try to put every dummy variable. This is known as dummy variable trap. So how to avoid this trap? You have to leave one dummy variable always. You have not to include into your equation, right? We will see that part once we will start encoding. So now I will come back to the Jupyter notebook to explain the code is almost very similar to simple linear regression. Let's see that. Okay. This is the multiple linear, this is backward elimination. Okay. Now this is multiple linear regression equation, and we are using the startup data, that same data. when I taught machine learning around 3 or 4 years back, then I used to write code for dummy variable trap also, but 2-3 lines of code was there. But in the if you're using Google Collaboratory or new versions of the softwares, then the scikit-learn library has automatically implemented the dummy variable trap problem, automatically handling the dummy variable trap problem. So you need not to encode it like that, but I just wanted to explain you what is the dummy variable trap problem in the encoding of the categorical data, correct? And there is one more thing which is there. Earlier, we used to do backward elimination, which is, if there are, how many variables are there? Let's say this is our matrix of features, 1, 2, 3, and 4 independent variables are there, right? R&D spend, administration spend, marketing spend, and the state. Let us say there are 25 independent variables in some data set, or 50 independent variables in some data set. Whenever, let's say, you want to make a presentation to your authorities, let's say, if they have asked you to develop a machine learning model and you try to give information about 50 variables, that how those 50 variables will change, and let's say the profit is the dependent variable, how the 50 variables will change, what will be the effect on the profits. That will be whole, it will be all mess. It will be very messy if you want to include so many variables in your presentations or in your model, right? So some of the variables you have to get rid of, which are not contributing to the decision making. And how to eliminate those variables, we will do the principal component analysis and the linear discriminant analysis in the future classes. But there is one more statistical tool which we can use, that is the p-value method. You must have studied in your information theory class about the z-score, hypothesis testing, z-scores, and p-value. Based on the p-value, we can eliminate the variables, right? That method, that method which we apply for elimination of the variables, that is known as, actually there are 4 or 5 methods, but one of the methods is backward elimination. And I would have done the backward elimination, but the newer versions of the scikit library also takes care of the backward elimination, right? So for the time being, I will not do backward elimination method or how to remove the variables using the p-values, but we will do the dimensionality reduction in PCA and LDA and other algorithms, right? Not these simple tools like p-value method and so on. Here we will develop the simple multiple linear regression model, and let's see how we can do. And the data set, as I have already explained, the data set is a 50 startup company, expenditure and profit and loss statement, right? Expenditure, you can say, is the loss part, and profit column is also there. As usual, you have to import the libraries, you have to import the data set, and the data set is in my working directory, and that data set name of the file is 50_startups.csv file. And this is the same ilog function for creating the matrix of features and dependent variables. Okay, so if you print X, this will be the matrix of features, feature data, and you can also print Y, right, which is the dependent variable, profit statement. As I told you, it also includes one column, which is the 0, 1, 2, and 3. Third column means, because in Python, the index starts from 0. So 0, 1, 2, 3. The third column is a categorical data. So definitely you will have to apply the those 4 lines of code, which will take care of encoding the categorical data. I have already explained the same. We will not make any changes. Only change here it is required that it is the 3rd column where one hot encoding has to be applied. So this is the 3rd column, and rest of the things remain the same. So what it creates, because there are 3 categories: New York, California, and Florida. So it has created 3 columns, right? Which are dummy variables basically, and this is how the categorical data, and this is our R&D spend, this is our administration spend, and this is our marketing spend. This is the matrix of features. And since there is no missing data, so we'll not apply the code for the missing data. We need not to bother about that, because that will be a redundant code if you will apply that.
Sir, इसमें dummy variable starting में क्यों गए?
That does not matter, but the software puts them. You must have seen in your other codes also. So they shuffle it and place it on the first column.
Always मतलब first में सब हर बार first में लाएगा.
You do not do something else. They are most of the times put on the first few columns.
Okay.
Okay. All right. So then you have to split the training set and the test set. Test size used is the 0.2. So that's also done. Now let's try to see what is there in the multiple linear regression. As you all know now, that we have to first of all create the we have to import from sklearn dot linear model. We have to import this class linear regression. We have to create regressor as the object, and we want to fit the object with X train and Y train. We have to actually train our machine learning model on these two training, the X train and Y train data, right? So this will create the model, which is the linear regression model. Now we have to start predicting, right? Well, because our model is prepared, now we have to start predicting. How to predict the data? Dependent variable is of course the profit, and our model is ready. So we have to predict the X test. We have to input the X test, and we will predict, and we will call this as y underscore pred using the regressor.predict function method. We will try to predict for X test. The rest 2 lines of code are actually what is being done. This is the how many there? Okay, this is 103. Y predict and Y test. Okay, so if you will, the second line of code is that you are using the numpy set underscore print options function. Well, print options function. What it will do is that you are setting the precision to 2. It will give up to 2 decimal places. Otherwise, it will give lots of decimal places. It will give, so that will be a confusion. Up to 2 decimal places, you can restrict your precision value, right? Then what you are displaying is that this is, let's say, the predicted data, which is coming from this ypred line of code, and the second column is actually the Y test data. Because we have X test data, we are subjecting the machine learning model for X test, which is acting as an input, right? And we are using the model to predict it, but we have the values for Y test also, and we will try to compare the values, right? So this is our and how to do that? How do we want to present that comparison? That comparison we want to present in the form of 2 columns. So the comparison will be, so this will be compared with this one, right? So that's how the data needs to be presented. And to present this in this fashion, we will use the concatenate function of the NumPy, right? So we will print using this NumPy concatenate function, np.concatenate. What we have to concatenate now? Ypred, of course. Ypred will be giving us the values. We will create a matrix of length Ypred, which is number of values of the prediction, comma 1. So it will be a 1-column matrix using the reshape function. And the second function, second column is ytest.reshape. And we will take the length from the length of the number of rows from the length using the length function y_test, right, comma 1. So these two, ypred and ytest, will be put as 2 columns, or will be put as a matrix of 1 column, right? And this comma 1, if you put 1 here, this is the whole. See, this one is the argument for the concatenate function, right? This one. So if you put 1 here, then the concatenation will be horizontally. So this is concatenated with this one. If you put 0, then it will be vertical concatenation. So this is horizontal. This is for horizontal concatenation. So when you run this, what you see here, that this is the predicted profit, and this is the actual profit, right? This is the predicted, this is the actual. So values are, here it is little, a difference is there, but most of the values are. This is first value has been predicted quite well. Second is almost okay. Third is almost okay, right? This is fine. 113 and 116, 116. So that's how you can create the multiple linear. If you will have even more data, then you will see that the values that you will predict using this linear regression model will come very close to the actual values, right? So this is how the multiple linear regression can be developed, right? Using this 50 startup data. Now, what I have covered till now is the simple linear regression and multiple linear regression. There are other types of regression also. One is polynomial regression. In the polynomial regression, what will be there? Let me just show you the equation if it is, if I'm having the equation. Okay, so this is multiple linear regression. Are you able to see this PDF file? So this is the multiple linear regression.
No, sir.
Okay, wait. Probably it's not shared. Let me just. Okay, so this is now you must be able to see. This is the multiple linear regression equation. B0, B1, X1, B2, X2, and there are n number of independent variables we have taught. We have put in this equation. Now, what will be polynomial regression? It will be only one variable, but the equation will change to B0 plus B1 X1 plus B2 X1 square plus B3 X3 cube plus Bn Xn raised to the power n. So that will be a kind of polynomial regression equation, but there will be only one variable, which is X1, but the other terms will be raised to the power. First term will be raised to the power 1, second term will be raised to the power 2, and so on. So that will be polynomial regression, right? But I will share with you the code, but I will not explain the code here in this class because I want to cover the logistic regression. Yeah, it's there. Let me just show you the polynomial regression. So this is polynomial regression equation. Again, this is a separate data set, position and salaries. I will send you the data set also. So if you create this model, you will see that if you see the results, these are the observed values. The observed values, if you look at the observed values, and what you're trying to do in this graph, you're trying to model the observed values. You're trying to model the data using a simple linear regression, which to my understanding is not very best fit for these types of observed values, because the observed values are following a polynomial kind of chart on the chart. It's a clear-cut polynomial. So if you try to follow, if you try to model this particular scatter plot using the polynomial regression model, then you will see that if you for developing the polynomial regression model, you will have to import the polynomial features from sklearn.preprocessing module, right? And then you can create the object and so on. If you create that, now you see the blue line is quite perfectly, modeling these observed values. And if you compare it with the simple linear regression, which is probably not the best fit for this type of data. So this is, I will send you the code, you can run, and you can also see the classes used here. The important thing is that we have covered now simple linear regression, multiple linear regression, and polynomial regression to some extent. Then there are other type of regression techniques also, like decision tree or random forest regression, and SVM regression, support vector machine regression. But we will learn decision tree, random forest, and SVM kind of techniques for classification. If the time will be there, we will do for regression also, but we will certainly do for classification. Right now, I will stop sharing this screen because I want to start with the logistic regression. So let us now try to understand what logistic regression is. Okay, so this is the PDF file that I have made. Let's see what is logistic regression and what is the concept behind logistic regression. So this is the first equation is for the simple linear regression. The second equation for the multiple linear regression. Here I have put the equation for the polynomial regression also. Right now, if we have this kind of data, the crosses are the observed values. We have already dealt with this kind of data where the salary and the experience was plotted. And we know that this kind of data can be modeled with a simple linear regression model, right? With this equation, y equal to b0 plus b1 x1. So we know how to deal with scatter plot as shown in this figure. We know how to deal with this kind of observed values. But let's see if the data observed values follow this kind of trend. Now, what is this kind of trend? Let's say there is an email going to the customers about the coupon or about the product, about certain product. Now, after seeing that advertisement, the customer can buy the product or cannot buy the product. So if the customer buys the product, let's say, it is yes, and if the customer does not buy the product, it is no. And if we try to, and that will be that we can call it as action in terms of yes or no, and that can be put as 1 0 also. If 1 is there, if the customer makes the decision to purchase, and 0 is there if the customer does not make the decision to purchase. And if we try to plot a graph with respect to the age, on the x-axis if we plot the age, and on the y-axis if we try to plot the action, depending on the age, whether the customer is attracted for the for buying the, for making the purchase or not. So you can see from this graph that for the lower age people, maybe let's say up to the age of 25, they are making a decision against the purchase. But after that age, maybe up to 55 or so, they make a decision for yes, that means they purchase, and that purchase decision will be put on this graph as against the value 1. Right now, you see here, if this type of data is there where the decision is made only yes or no kind of decisions, right? Now, how to, what is there in between the data from 1 and 0? What is this? I mean, if you try to model this data using a simple linear regression, using a linear regression, so that will not be very effective. So looking at the data, even if we don't know what is going on, even if we don't know what is going on between 1 and 0, but we can know some kind of correlations exist, some kind of observation we can make, and that observation can be that the lower that the not buying decision is more close towards the left, on the left side, right? And making a decision to buy the product is on the right side of the graph, more or less on the right side of the graph. So that kind of observation we can make, but we cannot, of course, use the linear regression. So if you try to model this data with this regression line, so it doesn't look like the best approach, right? So that is quite obvious also. It doesn't look like a very nice approach. And if you look closely, there is certain kind of correlation that, okay, I have talked about this. So can we do linear regression to model this data? The point is, no, we can't do using the linear regression. So what can we do? Rather than predicting yes or no, so rather than because we are trying to predict either yes or no, but rather than predicting yes or no, can we attach probabilities? That what is the probability of making the purchase? Then we can cover some portion, because the probabilities also lie between 0 and 1. So what is the probability of corresponding to different ages that this customer will buy the product? So rather than predicting yes or no, whether the customer will buy or not, we can work on probabilities of purchasing rather than just the crisp values of 1 and 0, right? Then if you will try to attach probabilities from 0 and 1, now you can go from this side, you can go from not purchasing up to the purchase decision with certain probabilities. Now this bold curve that I have made gives us the probabilities of making the purchase for certain ages, right? And we can just remove this part, this line which is going beyond the horizontal axis and going beyond the one axis, right? And just squeeze it, right? Like this. Now, can we predict probabilities, right? Can we predict probabilities? Of course, we can predict probabilities. What is the probability of buying? We can make a machine learning model where we can predict the probabilities that this is the probability for this age that with this probability they will make a decision to buy or not to buy, right? Okay, so this is our linear regression equation, y equal to b naught plus b1 x1. Now what we will do with this equation is that we will apply the sigmoid function, right? Now what is the sigmoid function? This is p equal to 1 over 1 plus e to the power minus y. What we will do is that we will replace this y with b naught plus b1 x1, and we will get this equation, right? This equation is the equation for logistic regression, right? So, and the shape of this equation, if you try to plot this equation, the shape will be a little S-shaped point, right? S-shaped curve, right? To represent this kind of data. Now the question again is that how should we make, if we want to make, of course this will, we are attaching probabilities here, so we can get the probability values, then what is the probability of buying for this age or this age, right? The question is that if you want to make a crisp decision, how to make that? Okay, now what you can do is that to this sigmoid, to this logistic regression equation, what you logistic regression model, what you can do is that you can put a line corresponding to 0.5, right? Also, so put a line here. Now if the predicted probability, whatever the probability that you will predict using the equation that I have just shown, which is the equation for the logistic regression, using using that equation excuse me, when you will try to predict the probabilities, now if the probability is more than 0.5, you will say that it belongs to this class of purchase, making the purchase. And if the probability is less than 0.5, you will project it on the horizontal line, saying that it will not, the customer will not make the purchase, right? So because you have to ultimately make a decision either in favor of purchase or not in favor of purchase. Of course, you can attach the probabilities, but and you can predict the probabilities also. Now, if the probability is more than 0.5, you will say that it will purchase, and when the probability is less than 0.5, you will project it to the horizontal line. So it's a zero probability. That means no, it will not. The customer will not purchase the item. Now, so these are the predicted values, and why? So this is only the representation. So anything below 0.5 will be projected on x-axis, which is not buying. Anything above 0.5 will be projected on this line 1, which is a decision of yes. So this is what is known as logistic regression. So how the logistic regression has evolved. So we started with the simple linear regression, and we then tried to look at this kind of data. So simple linear regression is not a technique which is giving us the best fit, right? So then we did some manipulation, and we say that we can find out, we can predict the probabilities, that what is the probability of different ages of buying or not buying. And based on that intuition, what we have done is that we have used the sigmoid function, and we have modified the simple linear regression equation like this, and we get a S-shaped curve, right, which will give us the probabilities of making a purchase or making a yes decision or no decision. Then we say that we want to know in a crisp manner. So we put a line here corresponding to 0.5, and if it is more than 0.5, we will say it is yes. If it is less than 0.5, it is no. And this is a kind of class. This can be used for classification also. Now, if you are predicting the probabilities, we are getting the continued values. Why it is not why it is not called logistic classification? Because we, as the theory has developed, and we have seen that we can predict the probabilities, all the probabilities we can predict. So then we are evolving a method of 0.5, either more than 0.5 or less than 0.5, to put our decision into two classes, either yes or no. So logistic regression, here it is used as a classification between two classes. So this is the background behind the logistic regression. And in the next class, we will take a fresh data set, and we will see that how the logistic regression can be used to model the observed values, right? So that part we will do tomorrow, how to develop the model for the logistic regression. If any questions are there, then please ask. If there are no questions, then I will close the class because it's time already 12:10. Okay, then. Thank you very much for joining. Thank you.